Hey, welcome to the next part of the journey in parametric equations and some calculus tacked on there. There's one more presentation after this, and I think it's an exciting one for you. But hey, what have I written here? Is this guy crazy? Let's make the points dance. What's that mean? Well, let's look around the screen, and you can see we're going to change the pair of parametric equations, which is describing our movement on the xy plane. Remember, this is a parameter t now, and t could be anything here. In this presentation, though, we're going to look at it as being time again. And over here, instead of just looking at the Cartesian equation of this pathway on the Cartesian plane there, we're going to look at its parametric equations, the connection of y and x independently. Back over here again, I've got it going all around the screen here, independently with t. Now, the idea here is, let's make the points dance. That's a Huddyism. The idea here to me is, as you'll see in the next presentation, if you could make x some function in t, and this could be itself a quadratic or a cubic, and so could y, can you see, or sense at least, that it could be that we could make the x and the y movements quite more complex than what we could with just writing a y equals a function in x type relationship, x cubed, x to the fourth, etc. They're actually pretty plain functions, but we could make the points dance a little bit around the Cartesian plane if we related each of them separately to a function in t. Okay, we're going to see that later on. You might give that idea some thought. Okay, let's go back now and review what we've done down here in the last presentation. Okay, we had two yachts, if you remember. One was at the point -10, 4, that was A, and it had a velocity vector 2, -1, so it was down here somewhere, going like that, a bit hard to draw on the screen. And vector B here was for yacht B, which was 3, -13 down here, and was travelling with a velocity vector -1, 3, something like that. So we had this yacht going up there, if you remember. So what we said about these two was that as time, if you consider t in these parametric equations to be time, and therefore this was a velocity vector here, we found that the rate of change of x prime of t was 2, and y prime of t was -1. And this, we said, was a pair of uniformly varying quantities with time, because its derivative with respect to time was 2 and -1. So as time went by, the boats had a constant velocity here, each of them. And the pair of uniformly varying quantities down here was also here -1. That was the rate of change. That was how they were varying with time, and 3. So that was the velocity vector. Okay, now do you get it? What we're doing here is looking at x and y variation separately from each other, and discussing whether with time or with the value of parameter t, does it change in a constant fashion or not? I think what you will see in a minute, let's have a look up here, I think maybe this will not change with constantly with time. Let's have a look and investigate all that stuff. And here it is, of course. Screen clippings here, just a few clippings from Hayes and Harris publications. So it'd be good to get their book on specialist math there. So let's have a look at that pair of equations that we had there. One is a linear variation, x varying linearly with t, and the other with quadratic variation, t squared. And so let's substitute values in. T is 0, we get this point, 1, 3. Substitute t is 1, we get 3, 6, etc. So we would get this plot over here for various points in time, and we just plot it out and say that that was the pathway of the body. Notice technically at this stage t does not actually have to be time. We are going to, in this presentation, consider t as time, In the next presentation, we've got something interesting coming up called Bezier curves, and t may or may not be equal to time then, or representing time then, that variable within the system. Okay, get the idea. We can plot that out. We've done a bit of that with the yachts, and we expect a curve here due to this business here. Okay, a quadratic, you can sort of see that, but let's investigate why that happens. Come down now, and I want to show you how to draw the plot without just integral values. Obviously you could put in t is 0.1, 0.2, etc. But on the graphics display calculator, and I'm using the Casio 9860 Plus here, you can do it much more neatly, and of course you can do it with a computer package, and that's mentioned in the Hayes and Harris book on specialist maths. So let's have a look at the calculator here. If you go to graph mode and hit that, you get the graph selections here, and we want to change the type of function to parametric. So we want that, so you need to come in here to F3 there. Go in there to F3 and hit that, and you get this window here, and there it is, Palm. That one. Oh, Parmigiano. Wouldn't mind one of those. I'm a bit hungry at the moment. Oh no, that's not what it is. If you hit F3, underneath there, you will see it's parametric. Okay, it's standing for parametric equations. And you can see in these two lines, you can put in a pair, x of t and y of t up the top there. So let's do that. Come across to this window over here now, and if you up the top there enter 1 plus 2t. Can you please notice down here with our variable x theta t, now it's off the screen here, but there is a button down there that you've been using for x. It's got theta and t on it, so it's the same button for the variable as we used before to get 1 plus 2t and 3 plus 4t take t squared. So I want you to try and enter that in your calculator using this same variable button, but because it's in parametric form on the calculator, it will enter t here for you. Now you must shift F3 now and go to view window. And if you go to view window, we get this one, and I've scrolled right down. You might never have seen this, but off the bottom of the x and y scales is this bit down here. So you've got to scroll right down and specify what values of t you're going to want the calculator to work with. So I've gone from -6 to 6. Okay, now that's not y is -6 and 6 or x, no, it is value of t. So when t is -6, it will plot the point, whatever that is there, for the y value. Okay, and so on. So we're looking at, we're looking at the value of t as the variable here to control the view window, not x and y. So you can see by going from -6 to 6, I haven't got the whole parabola in here. Okay, so do you get it? That's going to be important later on, particularly with Bezier curves. So you might just have a go at that and see how you can play with that scale and extend this graph. Okay, let's go on and see more about this function and see what we can do. So here we are. We've got x is this and y is this. Let's look at the rate of change of x with respect to t, not with respect to y, as you might have done in other courses, dy by dx and that sort of thing. So here's the rate of change of x, get the derivative of this. Derivative of this is 0. Derivative of the expression 2t, using the x to the n rule, is 2. The derivative of y, derivative of this part is 0. Derivative of this is 4. Derivative of neg t squared is neg 2t, using the x to the n rule. Remember the rule here then, if you have a function in t which is t to the n, then the derivative is n t to the n take 1. Commonly defined in xland, y is x to the n, then y by dx is n x n minus 1. All right, so you know that. So now, if t represents time, then we have a velocity expression, don't we? The rate of change of the x coordinate with respect to time will be the velocity in the x direction, the x component of the velocity, and the derivative of y with respect to time will be the y component of the velocity. Okay, so here we are, we have this velocity vector, and the first thing we notice here, I think, is that it won't be constant with time. As time varies, the y component will be different. It looks like the x will always be 2 for every unit in time. Let's say every second it will move 2 in the x, but it will move a different amount in the y depending upon the t. Let's have a look at the consequences of that. Come down here now and let's have a look. Here we go. So putting in t as 0, 1, 2 again, as we did before, but this time let's plot the velocity vector. Hey, look at this, it just changed. Hey, look, it changed again. Hey, it changed again. And that's because the y expression is showing, the derivative, sorry, is showing a dependence upon t. And that y component will vary right the way through there. And if we plot them, we get something like this. For the first one, 2, 4, that's the velocity vector at 0 time. And then at 1, here we go, at t is 1, oh, we haven't got t as 1, sorry, over here is t is 3. We've got 2, hang on, so let's have a look here, what have we got? This is at t is 3, they've drawn that. Oh, that's interesting. That's 2, 2, that should be at t is 1. Oh, that's all right, this is t is 1. This is x is 3, and that is obtained when t is 1. That's right. You nearly got confused there. So it's 2, 2. When x is 2, when t is 2, x is 5. Okay, t is 2, x is 5, and the velocity vector here is 2 north, parallel to the x-axis. Looks like that's going to be the same as with our usual derivatives here, where that's the turning point of the graph. Okay, parallel to the x-axis. dy by dx will be 0, maximum of the function. Okay, and so on. So we can actually plot the tangents, we can plot the velocities, and it looks like they're tangents to the curve. So what about that? Why is the velocity vector a tangent to the curve? And it's changing all around there. That's interesting. I wonder if that's just an anomaly here, or whether we can actually prove that these are tangents. Sorry about that, I've got to get rid of that. That these are tangents. Can we actually prove that velocity vectors are tangents? All right, well, let's come down and try and do it. And first of all, though, let's have a look and just remember that if you're looking at the speed of the particle around that figure then, that is the size of the velocity. Okay, the size of the velocity vector, which is the square root of the x component squared plus the y component squared, where these are the rates of change of x with respect to time and rates of change of y with respect to time, or rate of change. Okay, well, let's have a look at the proof now. Oh, we could have skipped a bit there, so come back up here. All right, so here's our problem. It looked like they were tangents, and we're going to aim to prove that now. So first of all, if we're looking at tangents, we need to look at the slope function for the curve. That is, well, how do you get the slope of the tangent to the curve? Okay, now the slope of the tangent is given by dy by dx. And so what you can say here is, let's try to find dy by dx, but we could say dy by dt is dy by dx times dx by dt. The chain rule, now we don't do that in this course. It's assumed that you've done some fundamental calculus. Maybe we should just pause the presentation now, and I want you to see if you can prove that, because that's where our starting premise, and that's very, very important in this discussion. So pause it and have a go. All right, coming back, I want to try and write down some sort of little proof here. Consider the right-hand side, dy by dx times dx by dt. Now, let's have a look at what that really means. Dy by dx is the limit as delta x tends to naught of delta y on delta x. Delta meaning small increments here. In maths, we use that symbol. And here, dx by dt is delta t tends to naught of delta x on delta t. Okay, but what we can say is as delta t tends to naught, delta x tends to naught. Why? Because our x is a function in time, here a continuous function in time. So let's change all the limits to limit as delta t tends to naught. So here's the limit as delta t tends to naught of delta y on delta x times delta x on delta t, using a common limit statement out the front. Now, we can at this stage cancel those, because delta x stands for a small increment in x. Notice we can't cancel, come back over here, can't cancel dx's here. They aren't actually separate terms multiplied or divided there. They represent these limits. So you really must go back to this level and say, well, I can cancel those increments, and you could draw this nicely on a graph. Okay, and so what have we got now with this? Limit as delta t tends to naught, delta y on delta t is dy by dt. That's our definition. Okay, so this is as required now. We wanted to prove that dy by dt was dy by dx, dx by dt. Okay, so we've gotten that. Now we can rearrange this. Well, first of all, let's write a little bit of a symbol here. Call y dash dy by dt and x dash dx by dt. I would prefer y dash t and x dash t, just reminding ourselves that the derivative here in the y and the x are with respect to time. Okay, so here we can say, let's rearrange for this. Dy by dx is y dashed over x dashed, or dy by dx is the same as y dash t over x dash t. What's that saying? Let's just unpack that a bit. So here, the slope of the tangent is equal to y dashed over x dashed. But why do we say that that's tangential? Let's look at what does y dashed over x dash mean. So the velocity vector is x dash, and here y dash t, let's put it in t's. So here, there's the velocity vector. There's our velocity vector. Y dash t over x dash t is the slope of that. We should put that in here. The slope of the velocity vector is equal to y dash t, y step over x step, if you like, change in y over change of x, change in x. So here, the slope of the velocity vector is equal to the slope of the tangent. I think you really do need to unpack the fact that the slope of the velocity vector, to be tangential, has got that slope. The y component over the x component is the slope in the conventional coordinate geometry world there. Okay, so do you get it? This is very, very important for later on. The idea that in this situation, you have got the velocity tangential to the path, and you should be able to prove that. Very interesting maths there. All right, come on down and let's see if we can use this in some way. And here's a little example from Hayes here. So we start off with two particular expressions of x with time and y with time. And it represents the flight of an arrow now, fired from a tree by Robin Hood. Oh yeah, that's a good one, isn't it? It's quite humorous, that. I think it's Robin Hood, isn't it? I'm not sure now. Anyway, let's wait. Y equals naught is ground level, and t is time here. So we should say that, and t is greater than or equal to naught. How high in the tree was Robin when he fired the arrow? What was the total time of flight? How far did it fly? What was the maximum height, velocity? All right, let's go through and have a look at this, all of those things. So just read those through and see what you think. Okay, let's have a look at the initial position. Initial position means at starting time t is naught. So substitute t is naught back up in here and you'll get the point 2,7. So what does 2,7 mean though in this context? Let's have a look. X is horizontal, y is vertical. So at naught, he was 2 meters up in the tree. It was the y value you wanted here. Okay. And that tree was what? Out here somewhere. so that it was actually 2 metres in the x. So he was up here somewhere 2.7. The measurement of the x value for t equals 0, it was already 2 metres from the origin of the arbitrary axis that we put in there for measurement. Okay, now what was the total time of flight? So you've got to find out when it landed, total time of flight. So let's put the y value now equal to 0. Just keep in mind the context here. X is movement horizontally, y is vertical movement. So it's got to come down to the ground. So we've got this equation and then just come down a little bit here. And if you solve that, and you could do that on the calculator, I suppose, equimode, and you get these two values. Notice we're using 4 figures here. Usually at the end we'd round off to 3, so you must carry at least 4 through your calculation. So there are 2 values according to this mathematical model. Just remember now, here there's that one, and also the model will say there's a 0 there, but past this point in time, this is not applicable in the context of this question. So this is an aspect of modelling. We've been able to make a mathematical model of the actual path, but it is also defined for other x's, or you have other x's and t's there that won't be allowed in the context of this problem, okay? Because you can't get negative x and negative time to come over here. All right, so here we are, approximately at that time. Now the next thing we want to do is to say, well, hang on, what was the next question? Part C was, what was the range of the arrow? Okay, and what was the maximum height? What was the range of the arrow? So the range of the arrow is going to be the y value. So here, what have we got? We can say here, the range of the arrow was the x value, so x of t. Okay, so substituting that time value in the x expression, you get 150.85. Okay, so just remember there, nearly messed that up. X is the horizontal, so that's the range of the arrow. That's the x distance. Okay, so the maximum height, well, maximum is when the derivative is 0. So the maximum y implies you want its derivative to be equal to 0. So there we are. If we get the derivative, we find we get this. Oh, that's an interesting number popping up there, isn't it? I think we recognise that. We'll do a little bit with that in a minute. So therefore, we put that equal to 0, and sorry about that, and we get 47 metres. So the maximum height is that, 47, approximately rounded off. You should put nearest metre here. And that's when t is this. Now, we really should affirm that that is the maximum. It's a little bit trivial in this case, but we should do that. So let's check it with the second derivative. And if we take the second derivative, here's the first derivative. Second derivative is neg 9.8, implies a local maximum there, doesn't it? And what have we got? Aha, that's the acceleration, isn't it? If we look at a moving body, the first derivative is the velocity, second derivative is the acceleration. And we'll give that a few ticks because that's the acceleration due to gravity. It's to the centre of the Earth, so therefore it's neg 9.8. Because y going up is positive, y coming down is negative, and this is centred down to the centre of the Earth, so it's neg 9.8 metres per second squared. Acceleration due to gravity. Okay, so I hope you can check that one out. All right, so what we want to do then is, now what's this next question? Let's just go back up and check E. What did E say? E said, what was the velocity of the arrow flight? The velocity of the arrow flight. So here, what we've got is putting those, looking at those derivatives. X prime t was 25, y prime t was that, so that's a velocity vector. Okay, and you can see this is constant, but the y component, due to that acceleration due to gravity, is going to vary with time. The longer the time that the gravitational force is acting, so it will change here the y component of the velocity vector. Okay, now the next one is what's the angle of which it takes off at the beginning. So if we look at the initial velocity vector, it's that when t is 0. If we plot it, that is 25 in the x direction and 28 in the y direction. Although he's up the tree, the tangent of this angle, 1.12 inverse tan, 48.2 degrees, rounded to 3 significant figures. Okay, so that should again be approximately signed there. So it's approximately 48.2 degrees to the horizontal. Okay, so we can do all sorts of things here which are interesting. So then when it's at the end of its path, so now that's part B's answer actually. How long is it in flight? So 5.954 y was 0. So if we put t as that in our velocity, that's still constant, didn't have a t in it. This is 28.9.8 t with t substituted in. So we've got that, and you see it's gone negative because with time that gravitational force has changed the direction upwards to downwards now, and the velocity vector has a negative y component. So let's draw it, 25 in the x direction and neg 30.349 in the y direction. That's meters per second. So what is the angle? So the angle from the horizontal is downwards now. So the tangent is opposite over hypotenuse, and it's 50.5 degrees in a different way, downwards from the horizontal rather than upwards from before. So it meets the ground at 50.5 degrees, because at the instance there where it's meeting, well, we won't put it like that, instant when it meets the ground, these are the components of the velocity vector. Okay, and then finally, what is its starting or its initial velocity? So at t is 0, it's that, and its speed is that, therefore. The speed is the square root of the x component squared plus the y component squared for that velocity vector. So we usually put, you can use that symbol as well, 37.5 meters per second, and we usually use 3 significant figures by convention in this subject. All right, so look at the sort of things we can say about projectile motion. That's fantastic. So let's actually summarize that now and have a look down here. So in general, for the motion of a projectile, the position equations, displacement equations, if you like, are that. And we've seen why that's got to be g. Because on the first derivative, we see that it's neg 9.8, and on the second derivative, it is neg 9.8 in there as a constant acceleration due to gravity. So this is worth trying to remember this, that structure for projectile motion working in gravitational constant g, which is 9.8 meters per second squared. We'll talk about that in a minute. So if you want the initial position with that pair, put in t as 0, so it's always the numbers out the front. That's the initial position. And the derivative is constant for this one and dependent upon t for this other one here. So they're a pair of non-uniformly varying quantities. One is varying uniformly with time, the other is not. And of course, the derivative of each with respect to time at time position 0 is AB. So that is the initial velocity, if you like. Okay, the second derivative is 0, and the second derivative is neg g here. Okay, and so that's going to give you the vector 0 neg g, and that is the constant acceleration vector. So here it is independent of time. So this one is 0 in the x, there's no change there in the acceleration in the horizontal, and that's the old thing of dropping the bullet, isn't it? If you fire a gun and the bullet goes that way, or you drop the bullet, it seems unbelievable, but if this is perfectly horizontal, they reach the ground at the same time, because although this has got this horizontal component, that does not affect the rate of change in this direction, which is affected by 9.8 meters per second squared down there, the gravitational force. So you don't have to consider in that direction the horizontal component, just the vertical. Okay, so that's what we're getting at here. There is no acceleration in the horizontal in the x direction, just the acceleration due to gravity in the vertical direction. Okay, so here's a little picture of what's going on. So the starting point there are the two initial values in the pair of equations, and the velocity vector here, AB, and as we go around, so this is the important point here, that the x component is varying uniformly with time at a meters per second, and the y component is not. B take gt, units per second, meters per second, or whatever. All right, are you ready? I think it's time to have a go and see what you can do. Sorry about that, I've got to fix that. Okay, so come down here and let's have a look at 6C1 from the textbook, question 1 and 2, and they are similar questions. Any projectile motion is modelled by that same form, so keep that in mind, particularly now for question 3. Question 3 is an interesting modelling question. Again, this is a projectile motion though, isn't it? So same idea, so try and construct your equations there. And in 4 and 5. So there are only 5 questions there for you to consolidate your thinking about this parametric variation. It's very interesting, isn't it? I think of what you can say, bring in that other component, that other variable into the system of time now. Okay, let's have a look at the answers or the solutions here. Check them out. So there's 6C1 question 1 up to G. So make sure you're getting this all right. This is very important work. And then let's see the rest of G there. And let's have a look at question 2. Oh, can we get it all on? We'll just see if we can. Yep, we can get all question 2 on. And then question 3. I don't think we can get all that on there. Got a little bit down the bottom. So let's go down and look at D. And then question 4. 4's still coming. We've got a bit more down the bottom. Okay. Rest of question 4. And question 5. And I think that's it for question 5. Yep. Okay. Well, how did it go? I tell you what, there's something exciting coming up with Bezier curves. And just to give you a tantalising bit towards that, Bezier was really, I suppose, the founder of CAD design. So that's interesting, computer-aided design. So I hope you look forward to that. Practice up. I'll catch you in the next presentation. Cheers for now.